concept of these models and the performance. Again, we had this for image classification. If you put image in front of humans and ask them classify those image, humans basically have between 5 to 10% error in image classifications. And as we went through this model, there's a different version of the models over the years, and it got to the point that we finally surpassed the human level performance, and with models like ResNet and CNET, basically. Now, it's something that's really important is that these types of models that we outperform basically finally human level performance, so from the left, look at this chart from left to right. So on the left, basically, there are the earlier versions. And this here's a shallow models, means smaller models, basically. And that's the error rate that they have, 28.2, 25.8. And as you can see, this error rate went down to 3.57. But what has changed, and the change is the number of layers and parameters that these models have. So as you go down here from basically GoogleNet to ResNet, we have from basically 22 layers, we went to 152 layers. Right? So we increase the size of the model. The models becomes much larger, more parameters, but then all of a sudden we notice that, oh, there's a huge shift here. Now these models basically they can outperform, human level performance, or they can do a really good job in these certain tasks. Right? So that's a reality. We couldn't do this, we couldn't be this good with smaller models. We need much larger models, it's more parameters. Right. And the next basically breakthrough was the AlphaGo. Basically, I don't know if you followed that back then, but 2016 when AlphaGo came up, it's like basically using deep learning, we were able to officially basically play against professional basically Go players, human players, and machine basically deep learning was able to basically defeat human professional in this Go. And AlphaGo that's the Go game of Go basically is pretty hard. I don't know if I haven't played it, but I have watched it. It's pretty difficult, right? So there are lots of rules, there are lots of thought process through it in order to make the next decisions. So that was also a breakthrough. Then the other one comes around, like for example, image describing photos. We humans, we can do a really great job looking at the image. We can describe almost everything, right? But machines, being able to teach machine algorithm basically to do that, that's also like a breakthrough. Now we can basically do something like that. Basically, you can have models that you provide an image and they can describe every details in that image for you, right? And that's one thing is just to describing it, but think about if for an AI model, in order to describe, for example, the ground is brown, the AI model should have an understanding of what's the ground, what's the brown, and how these two work together, right? So you see the different dimensions of understanding. It's not just to trying to describing an image. It actually has proper understanding of everything here, and it could basically explain that image using those understanding. Right, so that those dimensions are really important. And the simple example for those dimensions is that, I don't know if you are aware of this, like embedding, for example, in NLP, that when you think word embedding, like for example, we say that king has a dimension, like as a vector. If you think about it, for example, like if let's say you have this 3D basically space, and you have this here, for example, it says king. This king is here, and then let's say, for example, queen is here, and these two are kind of like close to each other. I put them far, but it's kind of like similar to each other, so because they're really close to each other. And when you think about it, the model basically has learned king, has learned queen, and this has a vector space, and that vector space basically the model learned that, like for example, royalty has this direction. Everything in this direction means royalty, king, queen, I don't know, like basically anything that comes in that family. But then you also have like man or male, female, or like woman. And what does that mean? That means that the model basically has learned a direction in the space for gender, right? And that's why when you think about this, when you say that king minus man equal queen minus woman, because from the perspective, mathematical perspective, is that we have learned some vector representation, which is this direction means, for example, gender. This direction means royalty. So you should be able to do simple, basically subtraction or basically addition to basically generate something new. And in NLP, for example, we try to learn, depending on the types of model, different dimension, 128, 256. And overall, across this dimension, we are learning different definitions. In image is also similar story, that we are trying to learn different basically the dimensions, different basic understanding over the data. So we could use that to basically describe an image, right? So that's basically what the goal that we have here. Now, the next basically breakthrough was that this artery breakthrough that we were able to use, reinforcement learning basically to, write some sort of code that beats arteries, in certain games. And it was pretty popular back then as like a, reinforcement learning and then deep reinforcement learning basically, which was really interesting. Now, the next thing comes around the audio super resolution. When you have audios which are like have a bad resolution, and you can use basically AI or AI models to improve those resolutions. So for example, here this is an example of low resolution signal.
One is investment, one is reform.
And you can pass such a basically record to a model, and the model.
One is investment, one is reform.
You see, it's able basically to improve the resolution of the audio, which is really useful for certain tasks, or even probably you have done right now on your phone, or like when you edit images and you have bad resolution images, and you basically try to improve the resolution of the image, you just improve it basically to certain degrees. So those are all like possible now. And especially these days, code generation, there are lots of like code pilot, autopilots basically out there that they help you with code generation, despite the fact that there are some beliefs of like, hey, this just makes the engineers lazy. But the reality is that we are in the era of generative AI, and you need to learn to utilize this as part of your routine. Otherwise you will just fall behind the curve. Just try to use them, but also if you use it, try to understand, to learn it at the same time. It's not just to ask it to write for you, but if it writes for you, then you also understand what was written, how it was written, and that becomes some sort of like a training for you. There are some caveats to it, is that the reality is that you need to be sure that things make sense. Sometimes I have at least test this out. Some of the code that it generates, it's overcomplicated the problem. You could write it much easier. So those are the type of things that you need to basically take into account. The other one is video generation. So look at this video, for example. This is generated by AI, and what does that mean? So it's not just the video being generated. What it means basically that in order for AI to generate this video, it needs to understand the concept of wave, and when wave hits to the shore, like what's the impact of that, right? So those all need to be understood basically by the model, right? Or this one is pretty well done if you think about it. Just like we'll talk about the hands later. So when we build the AI basically video. Think about the concept of what's happening. From AI, it's understanding what is movement. What happens if you're in the water? Your hair, how does it move? It's not just building, it's actually understanding how these processes. Pretty cool if you think about it. I said I'm going to talk about the concept of the hand. There is this reality was like, for some reason, these generative models, they're doing really bad with fingers. It feels like they're really bad in generating fingers. Normally, if you think about, if you want to detect a fake video or image, look at the hands. You always find the extra fingers, one less fingers, or there are some deformed fingers that are happening. There are some companies that are doing a better job now, but always fingers are kind of like the hand is some challenge, for some reason. We can talk about that later. But the other one is that imitation learning, which is pretty interesting because it's kind of like a conditional generation based on the history that I saw. Could I take actions, right? And this becomes basically, in order basically to take action, in order to play this game, you need to basically understand those actions. What will be the consequence of these actions that I will take? It's kind of like basically a statistical basis based on the history, but also it has some meanings. And you could also look at this one, this by 2022 by Jenner. So the idea here is that you basically teach this model basically sees and learns how to pick items, like in robotic, for example. By seeing some examples, it learns that how to pick and how to basically arrange the items, right? And these are all happening by learning and understanding the movement, understanding the physics here is not just, I will pick something, it's actually understanding that how the trajectory of these movements basically work. Then it comes around the overall, if you think about generative models, image generation, data augmentation, text generation, music generation, drug discovery, speech synthesis. So all have been happening right now these days with generative AI. Lots of cool startups coming to market every other day. They all have doing something interesting. This is a website that definitely look at it. It's called This Person Does Not Exist. And every day, you don't need that. Okay. Every day it will post one image basically here, and these images are not real humans. It's being generated and posted online. So it was pretty cool. But the quality that you will see of the images that's being generated, of course, it's really important also to talk about that. I know it's like the concept of ethical concepts behind this. The internet is full of fake generated basically images, videos, and stuff like that. And it's really important that for people who's building this type of thing, just maybe watermark it to say that this is an AI generated basically image or videos. It's kind of like it. So it's not going to impact people's life. Let's go back here. All right. Then it came ChatGPT, which we basically call it the conversational AI. Now it can do everything from text summarization, language translation, code generation, content creation, customer support tutorial, Q&A. It can do all of this. Right? Anything basically is kind of like conversational, basically text related. It can do a great job for you. Right? Because it's not like that this has only learned to basically generate. It actually has learned the contents. It can hold basically a conversation with you. It can answer back. It can do certain tasks for you. So we have much better breakthrough with NLP and compared to image, at least right now. Most of the generative image, it's basically graphical basically model out there. If you ask them, it takes you much more try to generate a good image, like lots of prompting probably, in compared to an NLP based questions, because it's much easier to prompt. Like I personally tried to last semester to create one image for an MLOps course, and I talked so many prompts, basically passed so many prompts, and I couldn't convince. And one of the worst things these days actually exists. For some reason, image generation, they cannot put text in the image. They can build a really nice image, but as soon as you put a text in it, that text has misspelled or is really bad. Doesn't matter how much you try, you cannot fix that point. So there are some limitations, but at some point probably, we will surpass those also. And next comes around the books written by AI. It's like there are certain, this was at some point it got popular that some of the books becomes bestseller on Amazon, written by ChatGPT basically, and it got to the point that it got out of control. And now Amazon, for example, is a great job. That's what they're doing. They're actually removing any books that's written by GPT types of model or AI because of the copyright, basically. Because those information, whatever this model generates, so context comes from outsourcing someone else's basically data from the internet, right? Which is a great thing also to talk about again as part of the ethical AI is that use AI for everything that you think is helpful. Don't use AI for taking away someone's job that they are having fun with it. Like use AI for basically assistant or augmentation for tasks that humans basically enjoy. Maybe I'm an artist, and for example, what Photoshop does is like I'm an artist, and Photoshop gives you these capabilities that using generative AI to enhance the images that I'm generating, rather than trying to replace me and just click a button and get an image, right? Where it says there's a task that is tedious and humans, they don't like to do it, it's dangerous, it's like a tiresome. So maybe those tasks we can automate instead of basically just instead of having a human doing it, we do it by maybe a robotic or something. So those are considerations to keep in mind, augmentation versus basically automation, when to do that. And it should be based on that. What's the outcome? Who's going to benefit from that? Who's going to suffer from that? So you just need to have this ethical consideration. And this is also another book written by this of an author, which again was pretty popular, basically novel, basically written by AI. And all of this becomes really popular until that finally Amazon basically decided to remove all of those books from the marketplace because of the copyright violation. So this is overall after, there was introduction to Gen AI, and what we are going basically to talk in this course is going to be everything that we talked up to this point around, going to be lots of textual, basically based models, text generation, and then we go lots of image generation, basically types of models. There's going to be 2 parts for this class again. First 7 weeks is going to be more NLP based, and the second 7 weeks is going to be image based, basically. So, any question on that? Please do one thing, ask question in the class. Again, don't hesitate. As if you don't understand something, just ask question. I'm here to answer the question. So be sure that you're, you're communicating with me. If you have a question, just ask question. If you don't ask question, I assume that you understand the concept, so I might speed up the process, right? So if something doesn't make sense, just let me know. One of your friends asked question about the project. For the project, you can. Didn't want to stop that. For the project, what you could do, you can have up to 3 students per project group, because again, the projects are more like a theoretical types of basically research. Could be research, could be the proof of concepts, could be building a certain types of model, but it's not an application, So you don't need more than 3 students per group. So you need maximum 3 students. Decide on those ones yourself, but try to also be early enough in the game. So find out your teammates and try to basically figure out what you want to work on. So now what we will do, now we are going to start with the neural network, basically. And again, I know for some of you have passed the neural network concept, but for some other students that they haven't, so we're going to basically have this. So we're going to quickly, again, talk about perceptron. We saw perceptron in the previous slides, but overall, basically, the idea is that in this basically circle that you see here, let's assume that we call that a neuron. And a neuron basically has 2 parts, basically has an input. This is the input part, raw input, and it has an output, right? So the input, the first part, the left part of the model, this raw input, is basically, as we say, similar to a linear regression, is a weighted sum of the data that comes through. And the output part here basically is going to be some activation function over whatever was the input. And that's basically that activation function basically becomes some sort of a non-linear, it could be a linear activation function, but it's normally a set of non-linear basically activation functions. I don't need to go over this one. Now think about the concept of perceptron. It's just a refresher. If you have a vector, and so let's say this is a line W transpose X plus B equals 0, or W, it's like your decision line. W is your weight, basically your weight matrices, and by default we know that the W is perpendicular to the line. And in order to prove that, you can basically pick any 2 random points on the line, X prime and X boon here, And those 2 points are part of the line. So if they are part of the line, that means let me pick a different marker. Only when semester starts, we have better markers. That's the case. Because we know any point on the line will fall in this equation, right? So if you put 2 points, let's say w x prime and x sub, they are basically the same thing, right? So if basically you get rid of the b, that means w becomes x prime minus x basically. And what do we have? W times x prime equals z. This w times this becomes 0. So if w times this vector is 0, what does that mean about w? It's perpendicular, right? So if w is perpendicular to vector x prime minus x sub, that means w is perpendicular also to the original line that we have. So that's one thing. The second thing is that how to calculate the distance of a point to the line, and you can also basically use the same concept, and we basically drop the line the perpendicular. Now this line is parallel with this line, and using that concept, you can understand that the distance between any line and any point and a line basically comes from by replacing the point in the equation of the line, dividing it by norm 2 of the weights. That's how you find the distance. Now we're going to use this concept in perceptron, how to solve perceptron basically. So if you think about the perceptron, you have this data set D that has series of basically input and output or labels basically. And your goal is that to basically find this W and B to optimize for it. And what do you want to optimize? Here in perceptron, we try to basically minimize the distance between misclassified points and the decision boundary. And misclassified here, the objective function that you see. So yi is your label. Here in the perceptron concept, we have it as a 1, like 1 and -1, similar to SVM. You know, you want to be +1 and -1, not 0 and 1 in other classifications. So W transpose xi plus b is the value that you get for any classification. So if you have this point versus this point, and this is your decision boundary, any points above W transpose xi plus b should be positive, right? Any points below should have a negative value, right? But these points below have a label -1, these points above have a label +1, right? So if you classify this correctly, +1 times positive becomes positive. You have a negative behind it, becomes negative. If you classify this properly, also -1 times negative becomes positive. You have a negative behind it, also becomes negative. So if everything is correctly classified, this becomes summation of negative values, right? So, however, if you misclassified any point, that means a point that here now is here. This is a negative value, times +1 becomes negative. And there is a negative behind it, now that becomes positive. So that's basically the idea, the objective function here. So you have this positive and negative. If you misclassified, you end up with a positive, basically, value total. And if it's correctly classified, this is going to be a total negative. And your goal is that basically here to minimize this JW with respect to W. And how do we minimize that? We basically using something like gradient descent. And gradient descent, the idea is that so you have these parameters, you take a derivation with respect to the, from cost function with respect to the parameters that you have set it to 0 and try to solve for that. So if you take a derivation with respect to W, this is basically what you're getting. If you take a derivation with respect to B, this is basically what you get. And this becomes gradient with respect to W, gradient with respect to B. We know gradient with respect to B is in here a scalar. Gradient with respect to W is going to be a vector of the same length, same dimension that W is. So if you have D columns, for example, W has D columns. So your gradient also will have be a vector of size W, size D. And you use basically gradient descent, which is your parameter updates becomes your previous estimate minus learning rate times the gradient, right? And that's how basically the learning happens. These concepts are clear for everybody, like at least these parts, right? So now this was the idea behind perceptron, but there is this book came out in 1960 called Perceptron, which basically point out that perceptron cannot solve the Zohr problem. Okay, this cannot basically solve a nonlinearity, and this basically actually let's draw it. So what does that mean? So if you think about I have a data set, so I have these classes. I have 4 data points, right? And this is basically, let's say 1, 1, 0, 0, right? If you apply perceptron to something like this, what happens? The only decision boundaries you get is either this or this. It cannot learn this Zohr problem because it cannot basically solve this. So how could we improve this? How could we solve this? And that's why let's go to neural network. Let's put series of basically perceptron on top of each other, build a neural network that they can solve the problem, right? Now, when we go to higher dimension, we no longer work with vectors or basically arrays, and we go to tensors, all right? And tensor basically is a higher dimension version of the, there's arrays that we have worked with up to this point. Now, tensor, for example, this is an example of image. If you look at it, for example, has 4 channels. First one is batch size. That means every set of samples that goes to the model, how many that batch size means. Like, for example, I pass 64 image to the model at this epoch. So that's the batch size. Then you have width. What's a width of like a horizontal? This should be a width of the dimension. And this should be the next one is height. What's the height of the basically image? And then you also have, because an image has RGB, then you have the channels, which becomes the last one. What's the number of channel basically that image? So as soon as you go to higher dimension, then from array we move to tensors, and that's why, for example, you see TensorFlow. That's the whole idea. It's like then the main idea behind this neural network was that okay, we want to mimic this abilities the human have. Well, how are we going to do this? We are going to do this by basically building a stacking series of neurons on top of each other. This is again the definition of a neuron. Neuron has 2 parts. Z stands for the raw input, F is the activation function, and it gives you the output. And again, this is just simply a same thing as perceptron. It's just a weighted sum, or just a linear combination. And then you apply activation function to learn the nonlinearity, and then you have the output of the neuron. Now, why we use activation function is really important to understand that without activation function, neural network is just simply linear regressions after each other, right? So it's just going to be a linear problem. If you want to learn nonlinearity, nonlinear decisions versus linear, you need to use that basically those nonlinear activation functions, right? Otherwise, the model learns everything to be linear. This is an example of sigmoid, for example. Sigmoid, what we know about sigmoids, what it does, it basically squeezes the values between the range 0 and 1. If you use it, for example, for classification as an output, like I'm doing a binary classification, and I want to be sure that at the end of the model, for example, I will get a probability between 0 to 1 that certain is either class dog or, for example, is a class cat. So I need to use something like, for example, sigmoid, which squeezes whatever you pass to this range. Here, basically, at 0.5, it goes positive, negative, and that's you can consider as a naive threshold, for example. And the derivation of sigmoid is also basically given over there. You could have tan H function. What happens was that sigmoid has some downsides. It was like especially with vanishing basic concept because it squeezes the range. So tan H does a similar job. It just scales the range, dynamic range from 0 to 1 to -1 to +1, basically. So, and that's also the derivation for tan H. You could have something like a ReLU, rectified linear unit, which what it does by default, if value is negative, it returns 0. If it's positive, it returns the value. Right, so that's basically ReLU. There are different versions of ReLU because this one has some problem, like a leaky ReLU, for example, which has it doesn't return 0 at negative, it returns a slight variation. But this is ReLU, and this is going to be the derivation of the ReLU. One of the downsides is that at 0, the derivation is not defined, basically. But all of this, basically, all of these activation functions, they help you with learning, and we're going to see really interesting. This thing doesn't work. I need to click on it this way. So this is the Understanding Deep Learning book. It has some basically playground that's really interesting for you to work. For example, this is a linear model, as we can see. So you change the intercept, basically how the line is changing, right? If it's intercept or if it's actually the actual parameter. Now, if you go to loss function, for example, this is basically how those loss function will impact. Now let's go to here, ReLU. So let's understand what we are seeing over here. On top, first row, what you are seeing is that, so we have three inputs, x1, x2, x3. They are going through different three neurons, okay? So you have this neuron for x1, and that neuron has the following linear equation, theta 1, 0 plus w times x. And this is how you decide what's the theta 1 and w. So you play with this parameter. It's like a w and b here. You have a w and b, you play with that parameter. So data goes through based on that linear equation, and this is the line that you have. So the output of the first part of this neuron, this z basically, is the first image. That's the z. For the second neuron, that's the z. For the third neuron, that's the z. You have the control over these parameters. Now, what's the next step? Is an activation function, is some nonlinearity. In this example, we are applying basically ReLU. What does ReLU do? It basically, if it's negative, it returns 0, otherwise value itself. So when you have this line, anywhere that's below the line negative, it becomes 0. Anything above the line remain the same thing in both cases. Now you have the output of this, which is A, the activation map. So these are the output. Now we pass those, you have three, we say that you have three nodes here. So there are three basically output here, A1, A2, and A3. You combine these three using some weights again. It's like you decide, these are the weights that you are using, because this is a line. So this, what it does is multiplied by negative, so it becomes negative. This one remains the same. This one basically changes the slope a little. Now you have these three lines, right? So how we get the output of this, we do summation across these three, right? So you do summation, you start from here. So you have a positive comes here, right? Then this positive comes because up here, this is 0, here, 0, 0, right? So this remains the same slope. And what happens here is that now you have negative. So this becomes deeper, right? So it becomes deeper until you get to this point, because now you have upward. So at here, it becomes upward. And then this becomes 0, then this becomes higher up. So that's the overall, basically, how you pick these models, basically how to interact with each other. These neurons basically process the information, passes to the next level. You do like some weighted sum, and you get the output. Now, that's the same thing you can do, for example, for sigmoid. That's how the sigmoid activation function works, and that's how become the output. And as you can see, every one of these activation functions that you use, they adds different types of nonlinearity in your data. So your model will be able to learn different information from that data, right? I could go to, for example, this Heaviside example, for example, this what you be learning set of like steps, basically, So let's go back. Where were we? Go back. Okay, so the concept of neural network becomes like, okay, now we want to stack this. We want to stack them on top of each other. We want to stack them after each other. So when you stack these neurons on top of each other, that becomes a layer. And then you basically put series of layers after each other, and they share the information, the process passes it to the next layer. And that overall becomes the neural network that we basically talked about. So neural network has an input layer. The first one, you see this input. So the difference here is that the input to the model, there's data that you have, you actually present that as a layer by itself, like an input layer. The important part about the input layer is that it doesn't have nonlinearity. It just actual data. Every other layer, as you go, there are some basically nonlinearity that you apply, some sort of, but an input, you just have the input, input goes to the next layer. So the next layer or next layers, that's where we call latent layers or hidden layers, because they are like technically inside your model. And then at the end, you have an output layer, basically. Right? And in this example, you have these lines, and this line stands basically for weights, connections. So if you have like this neurons basically, and this neurons connect with these lines like that, on top of every line, you have something like a weight, and that weight stands for, it's just a simple, like if you think about the concept of linear regression, that's the weight that you have for multiplying with the data that comes from the previous node. So X here has a value, you multiply it by weight, goes to this one. This one has an output, A12. There is also weight on this line, you multiply this by that, goes to the next one. And same thing as we saw in that image, the playground, right? So the data becomes multiplied by some weights, and then you sum those weights together. And this becomes the weights of between two layers. So it's really, in this example, like let's say this is a fully connected, that means every node, if this is a layer L and this is layer L plus one, okay? Every node in layer L is connected to every node in layer L plus one, fully connected. Right? They all have connection with each other. Now, that means if you have 3 here, you have 3 here, basically you have 9 connections, right? So 9 connections, 9 lines, that means you have 9 weights, right? And we show those weights, WL, weights for layer L, is a matrix 3 by 3 here, for example. And the way that basically we have been showing those is that you, so SL stands for size of the layer. SL means that how many nodes are in layer L. So SL here is 3. SL plus 1 is also 3. So when you want to write the weight matrix, the convention written as like it's kind of reverse. So we first point to the node. So let's write 1, 2, 3, 1, 2, 3. So the first weight, which is this one, is WL. L on top stands for, this is the weight for layer L. But the indices are kind of reversed. So we first talk about the next node that we are connecting to. So which node we are connecting? Node 1. So we put a 1 from where? From 1. Right? Then which node we are collecting? So this line to node 2 from node 1. And then to node 3 from node 1. So it's kind of like a reverse, right? So this basically becomes W SL plus 1 times SL from the size dimension, because SL plus 1 is size of next layer, SL is the size of current layer. So if you assume neural networks weight, the matrix is kind of like the reverse version. So we first index the next node, the node that we're connecting to versus the node that we are in. Then we have a bias term. So technically, not that is necessary always, but you normally have a bias node that's sitting here, B, and bias basically is connected, let's say, to every 3 here. So node layer L has a bias which connects to next 3 nodes in the next layer, right? So this becomes a vector of BL1, BL2, BL3. The size of this layer is the size of next layer, how many nodes in the next layer, because you're connecting to the next layer. So it becomes SL plus 1 times 1, right? So that's the weights, and those are the biases. Then, and now we have all of this. So we have all these connections that we stack them on top of each other, they share the information. But how do we learn? How does the neural network basically learn? The whole process comes from 2 things. There's a forward process or forward propagation, and there's a backward propagation. In reality, in forward propagation, you don't learn anything. It's just propagating the data, because you have already some weights or random weights, or basically, and you just pass the data just with multiplications, activation. So there's no learning. The learning happens in the backward process. So in the forward process, input comes, goes to a layer, as we saw, goes weighted sum, activation, goes to the next layer, weighted sum, activation, and so on. At the end, last layer, you make a prediction, either classification or regression. And you also have, for example, this is like, imagine this is a supervised problem, so you have a label also. You have a cost function that compares your prediction versus the label, and it calculates an error. Now, the idea here is that we know that we have this much error. We're going to use that error to propagate backward and update the WB and all the parameters that the model had by, and the way that we basically do this, when we go backward, it's kind of like I always like to use this analogy that, think about a game of telephone. I don't know if you know that. So game of telephone, it's like if you start to sing each other's ears something and you pass that, propagate that information. And at the end, I will say that, okay, what was the last person? What did you hear? And I know what the first person said. I said, oh, this is this much off. So propagate it backward, like as a penalty. You look at the person behind you, say that, hey, the answer was this. You told me this, right? Hey, and that propagates backward. And that propagation, every person updates their knowledge on what mistake they did, right? What was the actual answer, what they did. And you also know that, hey, I made this mistake, but the person behind me was the reason. They told me this. So the idea of backpropagation is that you backpropagate, you send back that error and try to basically divide the error contributed amongst all the nodes. That says that how much you need to update your knowledge, your weights, your parameters, basically, because you led to this. And one of the breakthroughs that we had in neural network was that this was feasible for us to do because we do some sort of like a chain rule, basically, operation, right? Instead of, so what does chain rule mean? That means that if I want to update the weights or parameters of the first layer, this layer, with respect to error, I don't need to do a derivation from here to here, large derivation, because that's really basically expensive, so sometimes infeasible, right? So what we will do instead is that we do gradual backpropagation. So it's just as part of the chain rule. So I go to here. Now I have a knowledge. I use that knowledge to go to here and here and here. So you do a smaller, like a chain rule, a smaller backpropagation. And that's how neural networks are basically, we can train those. Because if we don't do that, you need to, sometimes the functions are, the layers are so far from each other. If you want to take one derivation, that becomes super expensive. Is that clear for everyone? So now, if you think about the relationship between two neurons, so you have neuron basically J and you have neuron I. Between these two neurons, there's a line, and this line is a connection, and it has a weight, right? What's the relationship between these two? The raw input to this node basically has WL, AL plus BL. So think about this. So we have one neuron here, right? This is neuron J. And this neuron, let's say, is connected to 1, 2, 3. 3 neurons in the next layer, right? And what's the connection? So we basically can see that let's actually, let's first do a reverse version. Let's say this is I. 1, 2. So the next layer node gets information from previous 3 layer, right? So think about this. When the error propagates backward, you get to this node and it says that, hey, you are responsible for this much error. So this node at this point knows how much they contributed toward that error, how much they need to update their parameters. But then at this point, they need to propagate that error backward. But you need to be able to follow the error. Follow the the forward and do a backward on that. So at this point, this node says that, okay, I got an information from here, I got an information from here and here. So it propagates the error in 3 directions, right? Because in the forward, if you think also, this also goes 3 directions. Now this node number 2, that got 1 propagation from node number I, it actually, if there is a node J also here, it also has a channel this way, right? So you contributed some information to every node in the next layer. So when the error propagates backward, you're going to get some basically like error, basically amount of error from every node in the next layer. And you need to use all those information to update your weights, not just from one node, because you shared information to different basically neurons. Now here, so basically Z of I is a summation of all this values that we are receiving. So if this is I basically, the input, raw input to I becomes a function over the summation of W. Let's say this is L, this is L plus 1, WL, let's call this A, J from 1 to 3, plus BLI. That's technically what's as a raw input, raw input goes to node I. Weighted sum of all these arrows. Every arrow has a W, every arrow carries a data from the previous node, the output of the previous node, which is A, multiplication, plus some bias term. Let's say this is a bias term, basically. Right? So that becomes the moving forward. And then when you think about in layer L plus 1, you have series of these on top of each other. Right? So this ZI is just for one node. If you have L plus 1 nodes, overall, you will get Z to be a vector of LSL plus 1. And you have Z1 all the way to ZSL plus 1. For every node in that layer, you have one raw input. So that's the vector of raw inputs, right? So if you go to, now what do we need to do to those raw inputs? We need to apply some nonlinearity to some activation function, sigmoid, the value, whatever. So then you will apply that. And now you also have and basically output of that layer after you apply the activation function, which will have same length as Z basically, right? So if you think about the activation function for this layer, it's technically going to be something like this in a matrix form. And if you could basically expand this, actually is going to be a function over a function over a function, because it's kind of like a, if you think from end to end, it's kind of like a nested basically connections. And so this is just an example of Z4 becomes W3, A3 plus B, and you apply an activation on it. Now, then it comes the output layer, the last layer in your neural network. And that layer is where basically so up to that layer, your neural network learns a representation of the data. And you need to convert that representation to a task-specific regression, classification, or something like that. So at that end, you use certain types of activation function on the last layer. If it's a regression, you want it to be a linear. If it's a classification, you want it to be, like, for example, softmax if it's multi-class, or you want to be a sigmoid if it's binary, for example. And then you need also, again, after all of that, after your last layer, when you make a prediction, you need a cost function to evaluate how good was that prediction. And also that's task specific. If it's a regression or if it's a classification, your cost function or loss function is going to be related with respect to the task that you have. So overall, if you think about forward process, data will flow through all the way to the end. Then you calculate basically an error, and you pass the error backward as like a backward propagation to update the weights. So the way that basically you update the weights is that you technically don't update the weights step by step. You need to, from the last, basically the prediction, where was the error, propagate all the way to the first basically layer, get all those basic updates, and then update all together. You don't do sequential update. You do all the way to the end, update the parameters using a gradient descent, for example, and then you basically continue, do a next forward pass and backward pass. So then you basically need, let's hear this example here. We do some representation for the cost function. So in this example, it's kind of like a regression problem. So this is going to be our cost function on the last layer. And this cost function basically says that whatever is the output of the last layer, the nodes in the last layer, minus whatever was the actual label, and you do basically Euclidean distance or norm2 basically among this. So it just basically tells you that what's an average, basically, so what's a square, basically, error here. Now, you have this square error. Now, this is your cost function. You want to use this to go back and update the weights that you have, right? So what you need to do is that first, we know this is the basically gradient descent. WL becomes the previous estimate minus learning rate times the gradient. Gradient of what? Gradient of cost function with respect to W which is the W that you are trying to update. It's important to remember when you deal with neural network, you don't have one W. You have W per connections, basically per between layers. So there are a series of Ws. So you need to, when you take derivation here, WL means W at layer L. Then you have WL plus 1 and L minus 1 and so on, right? So it's just, you need to do this with respect to all of those. Similar for B, which is the bias term. So now think about the last layer here. This one, J, which is a Euclidean basically distance. So you want to take a derivation. So normally in a neural network, the way that we back propagate in order to update the parameters. So if you have such a board, it's hard to basically clean it. So this is the cost function that you have J, right? And this is your last layer, layer N, for example. Let's say this is your last layer. So you had 3 nodes, and these nodes basically made some prediction, and you have cost function. So you have 3 different predictions, for example. And in this example, we have Sn, we call that here Sn. So you have Sn nodes. Now, your goal is that you want to propagate the error backward. So when you have J, J says, I have 3 errors. Error that comes from this line, error that comes from this line, error that comes from this line. 3 different errors, basically. So J becomes summation of those errors. So when you back propagate the error, in neural network, you calculate the error, like the derivation, with respect to input to the nodes. So that's the part that you want to remember. You do a jump like this with respect to inputs of the nodes. So you take a derivation of J with respect to Z, Z, which is the raw input. Z always stands for raw input here. So you take a derivation of J with respect to raw inputs of the last layer. So what is the definition of J? J is this function, HWX, like a minus Y, norm 2. And what's HWX, which is the output of the node? Output of the node is always an activation over the raw input to the node, right? So output of this node, this line, is an activation over the input to this node, raw input. So when we say J, which is this one, we basically, when we say HW, that's technically an activation over Zn minus Yn norm 2, 1 over 2 behind. You take a derivation of that with respect to Zn. That's the activation, right? We have an activation over the norm, over the basically raw input. So if you take a derivation with respect to Z, so you have a 2, 1 over 2, they cancel each other. You technically have basically A Zn minus Yn. Then you have a derivation of Zn itself, which becomes derivation of Zn. So that becomes the derivation of the basically this cost function with respect to raw input to the last layer. And that's important. There's a distinguish between last layer and every other layer. Because last layer, you have direct connection to the cost. All right, so the derivation is simpler. But every other layer after the last layer is going to be different because now you have all this connection that comes. Remember I said that the arrow is not just generated by one, it comes from how you propagate the information forward. So the gradient of the cost with respect to every, basically every raw input, we show it by sigma, and here that was the function. Now let's do the same thing for any other layer, except this was for the last layer, any other layers, right? And for any other layers, that's where we're going to use the chain rule. So basically, the chain rule says that if you are trying to calculate so you have this node I, okay? And then you have 1, 2, 3. You have these 3 nodes. Let's assume these are the last layer again, last layer nodes. So we already from from J, we already calculated the gradient with respect to raw inputs of this tree. That was what we did here. The gradient with respect to raw input. And this is the equation. Okay. Now we want to propagate that backward. And we say that the beauty of neural network is that you can do this in a chain rule. And what does chain rule tell you is that chain rule basically tells me that really, I don't like this whiteboards. Chain rule tells you that if I want to calculate the gradient of J with respect to raw input of I don't need to calculate this jump. I already have calculated up to this point. I continue from here, right? Basically, gradient of J with respect to raw input to node I in layer, for example, here n-1, because the last layer we said is n. This comes from how many arrows goes here backward, if you look at backward? 3, right? So 3 gradients, basically. So it becomes summation over J from 1, 2, 3, let's say. 3 nodes, next nodes that we are connecting to. And then you're going to break this jump into chain rule steps. How? We will say that this line, I can represent it as gradient of cost with respect to this, which is this arrow that I have, with respect to Z N I, that's what we have here. That's the first part, times gradient of Z N I, the raw input to this, with respect to the raw input to this. Gradient of Z N I with respect to Z N-1, I and J. This I is in the bottom, J is J. This is the definition of chain rule in neural network. So you don't need to calculate large gradients. You do it sequentially, and I use what I already have learned in calculating the next one, right? And if you try it out, it's actually going to be the same thing. Like for 2 layers, easy, try it out later yourself. Just do it direct gradient with respect to this one from J, and you get exactly the same value. And it's summation because there's 3 gradients are going backward, right? So that's what you see here. Now, this term, we already have it, is there, right? The second term, we want to calculate this gradient of this raw input with respect to the raw input of that. What was the relationship? Think about the relationship. There is an arrow from here to here, right? And the raw input to every node, what was it? Weighted sum of the outputs of previous layer plus a bias term, right? So this, if I have a node here, and this is layer n node 1, okay? Node 1. It has this area, this dark area, that's the raw input. And I have these nodes in the previous layer. All of these nodes are connected, correct? So what was this raw input? Zn1 is summation of, there's a W here, Wn-1. So this is a n-1, Wn-1, 1, I from 1 to 3, plus Bn-1, 1 for this node, right? So this is the definition of Z. You are trying to take a derivation of Z with respect to what? Zi n-1. Oh, there's a times, sorry, I missed something. W times the output of that node. What's the output of that node? Activation over the input to the node. And the input to the node is Z n-1 I plus a B. So what will be the derivation of this term with respect to Zin? Right? So it becomes a W. So this becomes technically Wn-1 I times derivation of that activation function with respect to Z, right? So that becomes times A prime f or a prime z minus 1, right? And we know, for example, that also depends on what activation function you use. We saw 3 of those and the derivation. For example, sigmoid becomes sigmoid times 1 minus sigmoid, right? So you already know the derivation of those activation functions. But overall, this becomes this term. So now I have this derivation. I already had that derivation. This times that becomes the derivation of the cost function, this line, with respect to this raw input. Right? So using this chain rule, now every step you go backward, you don't need to calculate the long jumps, basically. Now, if I have all of this, why we care about the raw input to the model? Because if I have the derivation to here, I can calculate the derivation with respect to W and B also. Because W and B, they're sitting in between, right? Same story. If I want to calculate the derivation of cost with respect to this W, Wn minus 1, 1, 1, okay? With respect to that 1W, I need to think about, you need to follow the arrow, the flow, right? So I go, where do I see this W? In here. That means in order to calculate that W, I don't need those. There is no connection. That W is only connected this way. I don't need even this. I only need to follow this, right? So I already have this part. Same concept, same chain rule, right? So I already know there's no summation because there's no other arrows. So the gradient of this with respect to Zn1 times gradient of Zn1 with respect to W and minus 1, 1, 1. So this, again, we already have it. We already have it here. Now you need to calculate the gradient of Z with respect to W. What's the gradient of Z with respect to W? A. Directly A, right? So this becomes whatever was this gradient times. So gradient of, straightforward, gradient of cost with respect to weight is simply gradient of cost with respect to the input of the next node times the output of the previous node. That's how you update the W. What was the output of the previous node times the gradient of the next node. Now go for B. If B is the same idea, but if you take a derivation with respect to B here, you get 1, right? So gradient with respect to intercept or B is simply the gradient with respect to this only, right? Because if you think about it, why gradient of B is like that? Because B, if you think about the concept of intercept or bias stem, is responsible to update the input to this node so it becomes more accurate, right? So if the input to this node has like a 20% error, like 20% as a penalty, B should get 20% because B was responsible for adjusting that 20%. Should be exact same amount. The bias stem basically gets exactly same gradient. Is that clear? Also, is the speed okay? I'm assuming that. Yes. Right. Okay. So and that's the same thing. W and B. Again, these are all have been written on your PDF, proven. So if you don't need to write from the whiteboard, they all have been added to your basic PDFs. You can also present that in a matrix vector multiplication, which makes it better for computers to do the calculation instead of writing the for loops, basically. So that's how you basically you can look at the learning a neural network input, forward pass, basically doing a loss function and doing the gradient computation in the backward process. And this is basically, you can look at the pseudocode for it. That's follow it if you want to write it, basically. That's how you do the backward process. So you repeat this, calculate all the gradients, sum all the gradients. After you're done, then you update. So you don't update once, you just basically go through a series of those, average the gradients, and then update the weights. So if you do gradient descent, you go over all the data points that you have, which turns out to be pretty expensive. Then we have additional solution becomes like a stochastic gradient descent. So that means instead of going through all the solution, you sample maybe M data point and you go through those M data points. Why this will work if I use sample of data versus all my data. Because if you think about it from the concept of gradient gives you a direction of movement, right? So it doesn't matter if I sample 1 or 2, it still tells me that go this way. You know, both using all data or a small amount of data gives you the direction of update. Using more data, maybe you get a better estimate of how much to update, but it becomes slower. When you sample, you still get the direction, but you can do it much faster, maybe sampling much quicker. So you actually end up in a stochastic gradient descent, converge much faster than a gradient descent. Sometimes getting even a better result, because gradient descent, you know, it tends to become pretty heavy. So concept of gradient checking, you can manually check your gradients to ensure that your model basically is correct. One way in order to do that is basically you calculate the loss, the cost for a given W plus certain noise. So here, this E vectors, E matrix that you see is technically, let's say I have this W between layer WL. And WL, we say, is a matrix size SL plus 1 times SL, okay? So we introduce this matrix E, which is the same size, SL plus 1 times SL. And I'm interested, and the only reason we do this, if you're doing it in matrix form, I'm interested to check the gradient of this weight randomly. So what I want to do is that, similar to the concept of masking, I want to mask out the rest of this. So how? I set everyone here 0 and a 1 here, for example. So when you, what I'm trying to do here is that I want to see what's the gradient of this. So how do you calculate gradient? You add a small amount to it and you subtract a small amount to it, right? So basically you do epsilon times this E. All of those are 0 except for this. So you have an epsilon here. You plus this with, you sum this with this W, so only this one becomes updated. And once you do subtract, and you divide that by 2 times epsilon, whatever answer you get, it should be pretty close to whatever gradient your model is giving you. If it's close, that means your gradient calculation is correct. If not, then you have an idea that there's something that you need to find out. Maybe the gradient calculation that you do is, or some part of your code, something minus plus, something is always going wrong, right? So that was for the neural network. Again, I tend to skim through it because I feel like assumption is that you have some knowledge for this course. But again, if you don't have, that's fine. Just read the contents that you have. There are enough examples for you over there. And if you had questions, just reach out to your TAs and we will be there to help. Okay. Now, the next thing we're going to go over is going to be optimization techniques, which is pretty important. The optimization technique is that how we optimize this model is just they impact the learning of your model, right? Easily choosing a wrong optimization technique could easily lead to a local convergence or bad convergence and getting a bad result, basically. The first thing we're going to talk about is called Jacobian matrix. I assume you're all familiar with Jacobian matrix in your machine learning course, at least. Basically, when you do partial derivation, the first order of derivation gives you the Jacobian matrix. This first order, partial derivation. So if you have a matrix W, if you do a one order derivation, your gradient becomes a matrix of the same size, right? So that first order of the derivation is called Jacobian matrix. So Jacobian matrix, it gives you the information about the direction of moving. So you use basically the Jacobian for example, in gradient descent, we use that. It gives you the direction of movement and magnitude of movement. Then you have the second order, basically, derivation, which produce a Hessian matrix. So that's the second order derivation. Hessian matrix, the difference here is that it becomes a square matrix at this point, okay? And that means if you do one order derivation, becomes basically Jacobian. Second order derivation, it basically gives you the Hessian. There are some benefits of doing a second order derivation. So second order derivation or Hessian gives you information about something called a curvature. Curvature, basically, if you think of a line, so if you think a line like this, curvature of the line tells you that what degree, how much I basically need to extend this line to change it from a curve to a straight line. That's the concept of curvature, right? So why we talked about the Hessian is that the problem with Jacobian is that your model easily can stuck in some local or basically some flat regions, right? And when that happens, so think about something like this. Imagine you have this cost function that looks like this. And your model basically, this is, let's say this is flat. If you use Jacobian, your model basically falls in this region. And based on that, you try to just update, go left, right, for example, right? It's flat. And you have some definition in your code that after 10 epoch, for example, if it didn't update, stop the learning. So the code the model updates, it doesn't get out of this flat region, and then it will basically stop. So you never actually learn. So that's the problem with something like Jacobian. So when you do something like a Hessian, the idea is it gives you more information that hey, this is a flat region, for example. You can maybe basically progress faster through it. So it gives you some information about how to basically get out of these scenarios. Now, there are techniques that we are using Hessian as part of the optimization. So by default, we have talked about gradient descent. You have something like quasi-Newton methods that they use this Hessian. You have, for example, something like a Newton method, as I probably have seen that in machine learning course, but we're going to quickly see that. Those are using they're using the second order derivation. But first, we're going to start with a technique called momentum as part of the optimization. So it's pretty useful technique. What momentum does, think about it, it uses the previous accumulated gradients in order to move. Okay, so if you think about the gradients, and gradients only uses the current gradient. Where am I now? How much is my gradient? I use that to move. Momentum keeps track of past. How much was my gradient previously? Right? So it has two terms: accumulation of the previous gradients and the current gradient. So that's the term you see. Beta is a parameter you choose for your momentum, like hyperparameter. BT is the accumulated gradients from previous steps, plus 1 minus beta, right, times current gradient. So you decide how important is beta. If you make your beta larger, you give more importance to the previous gradients, the accumulation. If you make beta smaller, you give more importance to your current gradient. What's the benefit of that? The benefit is that if I stuck somewhere here, right, because I keep track of previous gradients, I know I need to take a bigger jump, because now the updates, it becomes previous values plus the current value, so it becomes bigger. So it helps you to get out of scenarios of like local minima or flat, basically, region. Now, and then at the end, you update similar like gradient descent. Parameter minus learning rate times the gradient. And the gradient comes again from this momentum, basically, term. Okay, so that's momentum. And this is basically how basically the momentum works. Basically, it just tends to converge much faster. Now, here there are some benefits again in this, which is the same thing that I just went over. It basically helps you to get out of those local minima or flat regions. The next technique here is like a Newton method. And Newton method, basically, you can look at it this way. So the updates, this WX over here doesn't matter, X is the parameter that you're updating, becomes previous estimate minus learning rate times second order derivation inverse. Second order derivation becomes the Hessian, inverse of a Hessian, inverse of a square matrix, times first order derivation Jacobian. So Newton method uses both Hessian and Jacobian, and that's basically becomes your update. That becomes your update. The way that Newton method basically works, it's technically it's using Taylor series expansion in order to estimate that those values. And there's so if you think about Taylor series expansion, we want to understand why this optimization techniques are working. So you are trying to basically estimate this value of xp, your current value plus some update. So you can basically approximate that using Taylor series. And this is the equation of xp plus f prime xp delta x, and so on, right? So that's from Taylor series expansion. Now, we want to understand that first, what does that mean before we try to take a derivation? So look at this line that you see the image. The black line is your actual cost function, right? So you are at x0, the red point, and you try to optimize. If you just use basically something like gradient descent, it slowly, you need to go basically left if you're going down, right? It becomes a slow movement. When you use something like basically Taylor series expansion, or basically approximation here, at every point, at point x0, the approximation of the function via Taylor series becomes this red line. Okay, so the red line, the first red line that you see on top, that's the approximation of the cost function with Taylor approximation at point x0. Okay, and that comes from this equation, basically. That's the Taylor series approximation. And how does that work? And why? What does that tell us? The Taylor approximation tells you that this is the approximation of the function. Okay? So you pick that information that you receive, and you find the minimum, the bottom curve of that approximation. So the minimum of this red line is here. You draw the line, that becomes your next movement. That's how fast you can go down. In compared to gradient descent becomes slowly, gradually goes down. So Taylor approximation gives you approximate, says that this is the approximation of this function at this point. This is the minimum. You need to move to this minimum. Then you go here, you do another Taylor approximation. You get the next minimum. You move much faster toward the minimum in compared to other techniques. Does that make sense? Yes.
Is it worth the compute expense?
No, we're going to, good question. We're going to get there. We're going to get there soon. So now, if you think about the Taylor series expansion, and we want to understand, compare it with the Newton method, where does that formula come? So you see, you have that approximation. Take a derivation with what are we trying to learn? We try to learn delta x. How much I should update, right? So you have this equation. Take a derivation of this with respect to delta x. So the first one doesn't have anything, it disappears. Then you have this term, right? Then there is a 2 and 2, basically this cancel. So then you have second order derivation, right? So if you do that and set it to 0, because you solve with respect to delta x, you basically get to this equation, right? So this derivation of this with respect to delta x, set it to 0, this becomes your delta x. And what does this look like? If you think about Newton method, what was the Newton method? The update was W minus learning rate times second order derivation of W inverse, which is the Hessian, times first order derivation of W. So what's the second order derivation of Zebun XP? 1 over that is the same as inverse of that. That's which is this term, right? Inverse of that times the first order, which is on nominator, which is your Jacobian. So that's how we basically have this Newton method. It's like a Taylor series approximations of solving that problem.
They use the same, right?
They're the same, yeah. So, and this just becomes, again, if you think about the Newton method, this is how basically it will work. Approximation, 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 and it helps you to jump fast. Now we're going to get to what your friend basically said here is that in a moment about the cost of this. But overall, think about the curvature also now. We talked about curvature, and what does curvature means is that at certain points you have different curvatures. You have a negative curvature, positive curvatures, and that curvature also is if it's 0 curvature, I'm in a flat region, right? So it says that you're already in a flat region, you can jump faster, right? If you're in a basically positive or negative curvature, then basically that means I'm in some sort of like a movement, some region. So basically I can go slower. If I'm in a flat, I will jump faster because I know it's a flat region. It's a curvature, like it's a line. I already know this is a line, it's not a curve, so I can jump. If it's a curve, then I go slower. Well, that's the idea of curvature here. Now, this is a different version of the Newton method called Quasi-Newton method. And as your friend basically says that here, calculating the Hessian matrix is expensive, right? And especially the inverse of that, it's expensive. So it's from the computational perspective, it's an expensive technique. When the larger it gets, it becomes more kind of like a difficult to do that. So quasi method basically is that it tries to basically iteratively approximate or calculates those Hessian values and Jacobian rather than at once. Iteratively tries to solve the problem instead of at once, because at once means that you take a derivation, you have the Hessian. This one does basically approximate it like slowly, gradually. So that's a quasi-Newton method. And as you can see, the comparison on the left and right, right is quasi, on left is Newton. It basically converges to the same place. Maybe at first it goes a bit wrong, but then it goes to a correct, basically, path. Then we have other technique, BFGS, basically, Bryden, Fletcher, Goldfarb, Shano, it's always one of those long names. And this one, what it does, so in the quasi, basically, we iteratively calculate the Hessian. This one says that you don't need the basically whole Hessian. I approximate it, basically, you know. I don't need to do all the calculation. Basically, I will approximate it here. And then you have a limited version of this, basically says that, you know, because if you calculate in the Hessian, you still need to store it. It has a cost, even memory cost for storing of those. So limited memory, basically, BFGS basically tells you that, hey, especially for large basically systems, it says that in order to basically storing this D by D Hessian matrix, basically only you're going to keep few vectors of that matrix. You know, instead of to having all of it, we're only going to use a few of that, basically. So these are all of these techniques basically helping you to do the same task, but doing it better, faster, you know, avoid stocking in a local or flat regions. And then there came a next technique, RMS prob. And RMS prob, basically, the idea was that the learning rate that we have should also update with respect to parameters. So basically, we try to update those learning rates, so it's not fixed, basically. So RMS prob, basically, what it does, it basically it's going to introduce a basically changeable learning rate. So you have this accumulated gradient, accumulated square gradient, basically. So you have the gradient, first gradient, which is the Jacobian. Then you do accumulated squared gradient using this equation, right? Then you basically using that your learning rate, your initial learning rate, divided by this value plus some epsilon, so to avoid basically dividing by 0, and that becomes your your updated learning rate. You use that learning rate and the actual gradient to update the weights. So in basic RMS prob, we use the second order basically accumulated gradients to update the learning rates. What does second order gradient tells us about the curvature? So you know that if I'm in a region that's flat, I need a larger learning rate. Am I in a flat, that region that the curve has a curve which is not around 0, so the curvature is not 0, then I need a smaller learning rate because I need to learn. I don't need to jump. So that's the idea in RMS prob, right? Does that make sense? So just account for if in a flat, your learning rate becomes larger. If I'm in a, you know, it's like a minima or some sort of like a region, then my learning rate becomes smaller. Then, so it has some benefits. One of the things about actually RMS prob is that it actually doesn't have much theoretical support. It was introduced as part of the Coursera. So it's not, there's no paper on it. It was part of the Coursera, their team introduced this technique and becomes really popular. So after that came a technique, ADAM, okay, adaptive basically momentum technique, which it becomes really popular, and is much more popular than other techniques, and it works really good. So what ADAM basically they have done, they have tried to basically combine the RMS prob and momentum technique. So RMS prob, which gives you the adaptive, basically like a adaptive learning rate, and momentum that gives you that accumulated, it's just using the concept of momentum to jump, have a larger gradient based on accumulated gradients. So it combined these two to build something called ADAM, and basically it has exactly equation of both two. So it has first order momentum and second order momentum. The first order momentum is that you're doing it over the first order of gradients. Then you have a second order momentum that you do it over second order basically gradient. And then you do some bias correction, and bias correction is that to have a better, smoother transition, you basically divide whatever value that you found from first order and second order by some basically 1 minus some value, just to be sure that is a bias estimate, like a bias update, sorry. And then you update the parameter using this similar concept of the gradient descent, but you update parameters like the delta W, for example, you have is going to be bias correction of the first momentum divided by square root of bias correction of the second momentum plus some epsilon, so to avoid dividing by 0. So this technique becomes pretty popular. It is right now kind of like a really common. Like I personally at work, all my models are always like ADAM. To be honest, like I barely try other ones because it's outperforms them by a good amount. But one of the things really we will see later is that some domains, depending on is NLP or image, sometimes you need to change this. Like ADAM might not work the best. You might better be doing some of the RMS prop, or basically we will talk about those as part of the labs. But that's the overall idea. So what are the advantages of ADAM? Faster convergence. It works on a basically large amount of data set. It's basically robust to noise that you have. Some limitation of ADAM is that it actually requires lots of like a tuning, it's hyperparameter tuning, and it might actually also struggle with non-convex optimizations. So there's also some challenges. It has, none of those comes as free. They all have pros and cons, but the reality is that you need to figure out which one works for your problem. Okay. Now, your friend here is about to point out like, what is it worth to basically do something like that? It's because when we deal with the second order derivation, the reality is that there are some challenges with any technique that does second order derivation. It becomes pretty expensive, and even memory